The universe is expanding galaxies, rushing apart at incredible speeds, but expanding into what? Most people picture space spreading outward like a balloon inflating into a room, but that's completely wrong. There is no room, no surrounding emptiness, no outside at all. The truth is far stranger. The universe is expanding into nothing because nothing exists beyond it, and understanding why reveals the deepest secret about the nature of reality itself. The impossible question. The universe expands outward in every direction, stretching the fabric of space itself. Yet when we ask what it expands into, we stumble upon a question that reality itself refuses to answer. This is not because we lack the tools to measure or the mathematics to describe the expansion. Rather, it is because the question contains a hidden assumption that there exists some vast container, some cosmic arena beyond our universe, waiting to be filled. But the truth is stranger and more profound than any container could be. The universe does not expand into anything because there is no anything outside of it. Space, time, matter, and energy, all of these emerged together at the beginning, and they define the entirety of existence. When we speak of the universe expanding into nothing, we are confronting the deepest property of reality, that the universe is not a thing inside space, but rather the totality of space itself. The confusion begins with our everyday experience. We see objects expand into surrounding space constantly. A balloon inflates into the air around it. A city grows outward into the countryside. Bread dough rises and pushes against the walls of its container. In every case we observe, expansion requires somewhere to expand into. Our minds, shaped by terrestrial experience, naturally apply this pattern to the cosmos. We imagine galaxies rushing outward like debris from an explosion, spreading into some pre-existing void. But this picture, however intuitive, fundamentally misrepresents what astronomers observe when they measure cosmic expansion. The expansion of the universe is not motion through space, but the expansion of space itself. The distinction appears subtle at first, yet it transforms everything. Consider two galaxies separated by 1 billion light-years. As the universe expands, the distance between them increases not because they are flying apart like rockets through a static void, but because new space is continuously being created between them. The galaxies themselves remain relatively motionless within their local patch of space-time. The metric of space, the very measuring stick that defines distance, is stretching. This stretching happens everywhere simultaneously, at every point in the universe, without requiring any external arena. When Edwin Hubble first observed that distant galaxies appeared to be receding from us in all directions, with more distant galaxies receding faster, he revealed this cosmic expansion. The light from these galaxies was stretched during its journey across expanding space, shifting toward longer, redder wavelengths. This redshift provided the first concrete evidence that space itself possesses a dynamic quality it can grow. But Hubble's discovery also raised the immediate question, into what does this growth proceed? The answer emerged slowly from Einstein's equations of general relativity, which describe spacetime as a fabric that can bend, ripple, and expand, but which does not require any background space to do so. General relativity treats spacetime as the fundamental entity. There is no stage upon which the cosmic drama unfolds. The stage itself is the drama. The equations permit solutions where spacetime expands uniformly in all directions, carrying galaxies along like dots on the surface of an inflating balloon. In this analogy, the two-dimensional surface of the balloon represents our three-dimensional space. As the balloon inflates, the surface area grows, and any two dots drawn on it move apart. Crucially, this expansion happens entirely within the surface itself. There is no into for the surface to expand. An inhabitant living on the balloon's surface, confined to 2 dimensions, would measure increasing distances between all points, yet would find no edge, no boundary, and no external space. Our universe operates similarly in three spatial dimensions. As space expands, distances between galaxies increase uniformly, but this expansion does not require, and indeed does not permit, any external realm. The universe contains all of space. Nothing exists outside, because outside is a concept that only has meaning within space. Asking what lies beyond the universe is akin to asking what happened before time began, or what is north of the North Pole. These questions assume a framework that does not apply. They attempt to extend spatial or temporal concepts beyond the domain where those concepts have meaning. This realization forces us to abandon our intuitive models. The universe expanding into nothing is not a failure of cosmic architecture. It is the fundamental nature of existence itself. Reality is not embedded in anything more fundamental. It simply is, and it grows. Nothing isn't empty. The nothing into which the universe appears to expand carries within it a structure so strange that quantum physics had to be invented before we could even speak about it coherently. Empty space, the vacuum between stars and galaxies, seems at first glance to be exactly that emptiness, a void, devoid of matter, energy, or activity. Yet quantum mechanics reveals that this apparent emptiness seethes with constant activity at scales far too small for us to observe directly. Virtual particles blink in and out of existence in pairs, borrowing energy from the vacuum for impossibly brief moments before annihilating each other and returning that energy. This is not speculation or mathematical abstraction. The effects of these quantum fluctuations can be measured in laboratories on Earth. The Casimir effect demonstrates this convincingly. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a tiny attractive force pushing them together. This force arises because the quantum fluctuations between the plates are constrained only certain wavelengths of virtual particles can fit in the narrow gap, while the fluctuations outside the plates remain unconstrained. The imbalance in quantum activity creates measurable pressure. The vacuum, therefore, is not passive nothingness, but an active medium filled with fleeting quantum events. These quantum fluctuations contribute to what physicists call vacuum energy. Even in the complete absence of particles, fields, or radiation, space itself possesses a baseline energy density. This energy cannot be removed. It is intrinsic to the structure of space-time at the quantum level. Calculations attempting to estimate the magnitude of vacuum energy have produced famously absurd results predictions that exceed observed values by more than 100 orders of magnitude. This discrepancy, known as the cosmological constant problem, remains one of the deepest unsolved puzzles in physics. Yet despite our inability to calculate its precise value from first principles, the existence of vacuum energy appears undeniable. Dark energy, the mysterious force accelerating the expansion of the universe, may well be a manifestation of this vacuum energy. Observations since the late 1990s have shown that the universe's expansion is not slowing down, as gravity would suggest, but speeding up. Distant supernovae appear dimmer than expected, indicating that space itself is expanding at an accelerating rate. The simplest explanation involves a uniform energy density filling all of space, a cosmological constant with properties identical to what we would expect from quantum vacuum energy. If this identification is correct, then the nothing between galaxies is not empty at all. It is filled with a dark, repulsive energy that pervades every cubic centimeter of the cosmos. This energy does not clump or cluster. It does not form stars or galaxies. It simply exists uniformly, exerting a negative pressure that pushes space apart. As the universe expands, more space is created, and with it, more vacuum energy. Unlike matter or radiation, which become diluted as space expands, vacuum energy maintains constant density. create more space and you create more of this dark energy in equal measure. This property drives the accelerating expansion, creating a runaway process where expansion generates more vacuum energy, which drives further expansion. The nothing into which the universe expands is therefore filled with invisible quantum machinery. Virtual particles flicker into brief existence. Quantum fields oscillate in their ground states. Dark energy exerts its relentless outward push. Far from being a passive void, this nothing actively shapes the fate of the cosmos. It determines how fast galaxies recede, how structure forms, and ultimately how the universe will end. The strange, active emptiness of quantum vacuum may be the most fundamental substance in existence, a nothing that is, paradoxically, very much something. Space creates itself. Space does not spread into pre-existing emptiness, like ink diffusing through water, but rather generates additional space from within its own structure, a process as fundamental as it is difficult to visualize. When the universe expands, it is not claiming new territory from some external reservoir. Instead, the metric of space-time itself changes, stretching the distances between objects without requiring those objects to move through any background medium. This self-creation of space operates according to the dynamics described by general relativity, where space-time responds to energy and matter, curving and evolving in ways that need no external stage. The mathematics underlying this process treats space and time as components of a unified four-dimensional fabric. Einstein's field equations relate the curvature of this fabric to the distribution of energy and momentum within it. Solutions to these equations include cosmological models where space expands uniformly in all directions. The Friedmann equations, derived from general relativity, describe how the scale of the universe changes over time, depending on its energy content. These equations govern expansion without invoking anything outside the universe. The growth of space emerges purely from the internal dynamics of space-time itself. Consider a simple analogy that captures part of this strangeness. Imagine a two-dimensional universe represented by the surface of a sphere. As the sphere grows, the surface area increases, and any 2 points on the surface move farther apart. Yet the surface itself remains complete and self-contained at every moment. No point on the surface can be identified as the center of expansion, and no point lies at an edge. The expansion happens everywhere simultaneously, intrinsic to the surface's own geometry. Our three-dimensional space behaves similarly. It expands uniformly, increasing distances between galaxies, without requiring a four-dimensional hyperspace to expand into. The expansion began at the Big Bang, when all of space was compressed into an inconceivably small region. At that moment, space-time itself came into existence, along with matter and energy. There was no before in any meaningful sense, because time itself began at the Big Bang. Similarly, there was no outside for the nascent universe to occupy, because space itself emerged from that initial singularity. As the universe evolved, space expanded rapidly, driven first by the intense energy of the early cosmos, and later by the gravitational dynamics of matter and dark energy. During the first fraction of a second after the Big Bang, a period known as cosmic inflation may have caused space to expand at a truly staggering rate. Within less than 1/trillionth of a trillionth of a trillionth of a second, the universe could have grown from subatomic scales to macroscopic sizes, increasing by a factor of at least 10 to the 26th power. This inflationary expansion was not limited by the speed of light, because it was not motion through space, but the expansion of space itself. General relativity permits space to expand as rapidly as its energy content demands, without violating any speed limits on particles or information moving through that space. After inflation ended, the universe continued expanding at a more sedate pace, governed by the balance between the gravitational pull of matter trying to slow expansion and the outward push of radiation and, later, dark energy. For billions of years, gravity dominated, slowing the expansion rate. Then, around 5 billion years ago, the density of matter dropped low enough that dark energy began to dominate, driving the expansion to accelerate once again. This acceleration continues today and appears likely to continue indefinitely into the future. The key insight is that at no point in this history did expansion require external space. The universe contains all the space there is. When we say space expands, we mean that the distances measured between objects increase over time, but those objects remain embedded in the only space that exists. The expansion is a property of space-time itself, not a motion into something else. Space creates more space through its own internal evolution, following the laws of general relativity without reference to any external framework. This self-generating quality of space represents one of the most counterintuitive aspects of modern cosmology, yet it follows directly from our best understanding of gravity and the structure of the cosmos. The universe does not need anywhere to expand into because it is the totality of where and when. It simply grows, adding to itself, creating space from space in an unfolding process that has continued for nearly 14 billion years. Faster than light, galaxies at the edge of the observable universe rush away from us at speeds that dwarf anything light itself can achieve, yet they violate no laws of physics, obey no impossible mechanics, break no cosmic speed limits. The paradox dissolves when we recognize what is actually happening. These galaxies are not racing through space like cosmic dragsters accelerating down some universal motorway. They sit relatively still within their own local patches of space-time, while the space between us and them expands. Space itself grows, inserting new distance between points that were once closer together, and this growth follows no speed limit whatsoever. Einstein's equations forbid anything with mass from moving through space faster than light, but they place no such restriction on space itself. The distinction matters profoundly. When a photon travels through space, it moves at exactly 299,792,458 meters per second. Nothing with mass can match this speed, and nothing, neither matter nor information, can exceed it. This speed limit emerges from the structure of space-time itself, woven into the fabric of relativity. Any object attempting to reach light speed would require infinite energy, making the barrier absolute. Yet when astronomers measure the recession velocities of distant galaxies, they find objects moving away from us faster than light. Some galaxies recede at twice the speed of light. Others race away at 3 times that speed. The most distant observable galaxies retreat at velocities approaching 3.5 times the speed of light. This apparent violation becomes comprehensible once we properly understand cosmic expansion. The galaxies themselves barely move. A galaxy 10 billion light-years away sits nearly motionless relative to the space immediately around it, perhaps drifting slowly due to local gravitational influences, but not racing through the cosmos at relativistic speeds. Between that distant galaxy and our own Milky Way, however, lies an enormous volume of space. As the universe expands, every cubic meter of that intervening space grows slightly larger. Each small increment of expansion adds only a tiny contribution to the overall recession velocity. But with billions of light-years worth of space between us and that distant galaxy, all those tiny increments accumulate. The mathematics describes this through the Hubble constant, which relates the speed at which galaxies recede from us to their distance. Current measurements place this value at roughly 70 kilometers per second per megaparsec. A megaparsec equals approximately 3.26 million light-years. So for every megaparsec of distance, recession velocity increases by about 70 kilometers per second. At sufficiently large distances, this relationship produces recession velocities exceeding the speed of light. A galaxy 14 billion light-years away recedes at approximately 1.5 times the speed of light. A galaxy 20 billion light-years distant rushes away at more than double light speed. General relativity permits this because the expansion involves no local violation of physics. Within any small region of space, nothing moves faster than light. An observer standing on a planet in that distant galaxy would measure the speed of light at precisely the same value we measure here. Rockets launched from that galaxy could not exceed light speed. Information transmitted from that galaxy could not travel faster than light through local space. Yet when we account for all the expanding space between that galaxy and ours, the cumulative effect produces apparent recession velocities far exceeding light speed. The speed of light remains an absolute limit for motion through space. Expansion of space operates under different rules entirely. This distinction allows the universe to expand as rapidly as its energy content dictates without contradicting relativity. During cosmic inflation, in the first fraction of a second after the Big Bang, space expanded so rapidly that regions now separated by billions of light years were once close enough to interact, despite the brief time available. The inflationary expansion far exceeded the speed of light, yet it involved no particles or information traveling faster than light through space. Observational evidence for faster-than-light recession comes from measuring redshift. As light travels through expanding space, the space through which it moves stretches, elongating the wavelength of the light. This stretching shifts the light toward the red end of the spectrum. The degree of redshift indicates how much space has expanded during the light's journey. Astronomers have detected galaxies with redshifts so large that they indicate recession velocities exceeding the speed of light at the time the light was emitted. These observations confirm that expansion operates independently of relativistic speed limits. The expansion continues accelerating, driven by dark energy. As billions of years pass, more and more galaxies will cross the threshold where their recession velocity exceeds light speed. These galaxies will not disappear suddenly, but their light will become increasingly redshifted, stretched to longer and longer wavelengths, until eventually no photons from them will reach us at all. The nothing between us and them will have grown too fast, creating an unbridgeable divide where space itself expands faster than light can traverse it. The vanishing act. Galaxies slip beyond an invisible boundary in space every moment, crossing into a realm where the expansion of the universe carries them away faster than their light can ever reach us, rendering them permanently invisible and forever unreachable. This is not some distant future catastrophe, but an ongoing process that has already claimed the vast majority of galaxies in the universe. Right now, as you consider this, galaxies are vanishing from the observable universe, their light stretched beyond detection, their presence erased from our cosmic horizon. The expansion of space does not merely move things apart. It actively severs connections, breaking the threads that once allowed light to bridge the gaps between distant regions. The boundary that galaxies cross is called the cosmic event horizon. This horizon marks the distance beyond which expansion outpaces the speed of light so thoroughly that photons emitted from a galaxy can never close the gap. Light leaving such a galaxy struggles upstream against the current of expanding space, making progress toward us, but never enough progress to overcome the continual addition of new space between us. The photon swims forever toward us, yet never arrives, trapped in an expanding medium that stretches faster than it can traverse. Current estimates suggest that roughly 95% of galaxies in the universe have already crossed beyond our cosmic event horizon. We can still see many of these galaxies because we are observing light they emitted billions of years ago when they were closer and had not yet crossed the boundary. That ancient light has been traveling toward us for eons, and it will continue arriving for billions of years more. But no light emitted from these galaxies today will ever reach us. Any astronomer living in one of those distant galaxies looking back toward the Milky Way, would face the same situation. Light from our galaxy emitted today would never reach them. The connection has been severed by the intervening expansion. As time progresses and dark energy continues driving accelerated expansion, the cosmic event horizon draws closer. Galaxies that are currently observable will cross this boundary and enter the unreachable realm. The light they emit today will be the last light that can reach us. Future civilizations, should any arise billions of years hence, will observe a much smaller universe. The rich tapestry of galaxy clusters and cosmic structure that we observe today will have faded. Only galaxies bound to us by gravity, those close enough that their gravitational attraction overcomes cosmic expansion, will remain visible. Our local group, containing the Milky Way, Andromeda, and several dozen smaller galaxies, will persist as a gravitationally bound island in an increasingly empty cosmos. Observations of distant supernovae in the late 1990s provided the first concrete evidence for this accelerating expansion. Type Ia supernovae serve as standard candles, meaning they have a known intrinsic brightness. By measuring how bright they appear from Earth, astronomers can determine their distance. When these measurements were compared with the redshift of their host galaxies, the results revealed that distant supernovae were dimmer than expected. They were farther away than their redshifts would suggest. If the universe were expanding at a constant rate, the expansion was speeding up. This acceleration implies that the universe's expansion will continue indefinitely, growing ever faster. Dark energy, the mysterious force driving this acceleration, appears to maintain constant density even as space expands. Create more space, and you create more dark energy. This property ensures that the accelerating expansion will persist, carrying galaxies beyond our cosmic horizon at an ever-increasing rate. The universe is not merely growing, it is growing faster and faster, creating an ever-widening chasm between regions that were once able to exchange light. The implications extend beyond mere observation. These vanishing galaxies represent lost information, lost history, lost possibilities. Any civilizations that might exist in those galaxies are being carried beyond our reach, not by their own motion, but by the expansion of space itself. If we wish to send a signal to such a galaxy, even a signal traveling at the speed of light, it would never arrive. The expansion would stretch the space between us, faster than the signal could cross it. These galaxies have not merely moved away, they have entered a domain that is causally disconnected from us, a region with which we can never interact, never communicate, never exchange information. Within our own observable universe, structure continues to form. Galaxies merge, stars are born, planets coalesce, life may arise on countless worlds. But beyond the cosmic horizon, a vastly larger universe proceeds along its own evolutionary path, forever beyond our knowledge. The observable universe represents only a tiny fraction of the whole, a bubble of visibility in an ocean of unreachable space. Everything outside that bubble might as well not exist, as far as any observation or experiment we could perform is concerned. The vanishing of galaxies serves as a profound reminder of cosmic isolation. We occupy a particular location in space and time, with access to a finite volume of the universe. That accessible volume shrinks as expansion continues, not in absolute size, but in terms of how much of the total universe we can observe or influence. We live on an island that is becoming more isolated with each passing moment, surrounded by an ocean of expanding nothing that grows deeper and wider, carrying away everything beyond our reach. What nothing means. The universe's expansion into nothing forces us to confront a concept that our language struggles to capture, that existence itself has no container, no surrounding medium, no external framework. When we use the word nothing in everyday speech, we typically mean empty space, a void waiting to be filled, a region devoid of objects but still possessing dimensions and location. The nothing beyond the universe is categorically different. It is not empty space, but the absence of space itself. It is not a void, but the absence of void. It possesses no dimensions, no location, no properties whatsoever, because it does not exist in any sense we can meaningfully describe. The confusion arises from our experience. Every expansion we observe in daily life involves something growing into something else. Water spreads across a floor, filling previously dry regions. Cities expand into countryside, converting farmland to streets and buildings. A balloon inflates, pushing aside the surrounding air. In each case, there exists a clear distinction between the expanding thing and the medium into it expands. We instinctively apply this model to cosmic expansion, imagining the universe as a growing sphere of space pushing into some pre-existing void. But general relativity forbids this picture. Space is not embedded in anything. It is the totality of where things can be. Einstein's equations describe space-time as a self-contained entity. The solutions to these equations that describe our universe, the Friedmann-Lemaitre-Robertson-Walker metrics, treat space as finite or infinite in extent, but never as embedded in a higher dimensional space. The expansion these solutions describe is an evolution of the metric itself, a change in the fundamental geometry that defines distances. When the scale factor of the universe increases, the metric specifies that any 2 points not bound by local forces will measure an increasing distance between them. This increase happens without reference to anything external. The analogy of dots on an inflating balloon captures part of this behavior. As the balloon expands, dots drawn on its surface move apart, yet no dot occupies a privileged position at the center of expansion. Every dot sees every other dot receding, with more distant dots receding faster. The expansion happens uniformly across the entire surface. Crucially, this expansion occurs entirely within the two-dimensional surface itself. An inhabitant of the balloon's surface, restricted to 2 dimensions, would have no access to the 3-dimensional space in which the balloon sits. For that inhabitant, the surface would represent the entirety of space, expanding without any external medium. Our universe operates similarly, though in 3 spatial dimensions rather than 2. We are like inhabitants of the balloon's surface, confined to our 3-dimensional space, with no access to any higher dimension into which our space might expand. The expansion we observe is intrinsic to space itself. General relativity does not require, and indeed does not allow, for any external arena. The mathematical framework treats space-time as the fundamental entity, not something embedded within something else. This leads to profound conceptual shifts. The Big Bang, for instance, is often misunderstood as an explosion that occurred at a specific location in space, with matter and energy flying outward from a central point. But the Big Bang happened everywhere. At the moment of the Big Bang, all of space existed in an extremely hot, dense state. As the universe evolved, space expanded, carrying matter and energy along with it. There was no center to this expansion because all of space participated in it uniformly. There was no edge because space was either infinite from the beginning or finite but unbounded, like the surface of a sphere. The question, what happened before the Big Bang, suffers from a similar misconception. Time itself began at the Big Bang, according to general relativity. Asking what happened before involves extending the concept of time beyond the domain where it has meaning. Time is a dimension of space-time, and space-time began at the Big Bang. There is no temporal framework extending backward beyond that point within which events could occur. The concept of before simply does not apply. Likewise, asking what lies beyond the universe attempts to extend spatial concepts beyond their domain of applicability. Space is defined by the metric of the universe. Beyond the universe, there is no metric, no geometry, no distances to measure. The phrase, beyond the universe, contains an internal contradiction. It assumes a spatial relationship beyond, in a context where space does not exist. The universe contains all of space by definition. Asking what it expands into is asking what spatial region exists outside all spatial regions, a question that undermines its own premises. This philosophical point has practical implications. When physicists model cosmic expansion, they do not include boundary conditions specifying what lies outside the universe. The equations describe the evolution of spacetime entirely in terms of the energy and matter within it. The universe is treated as a complete, self-contained system. Its expansion requires no external space to accommodate growth. Space itself is created through the expansion process, added to the existing fabric of spacetime according to the dynamics specified by general relativity. The nothing into which the universe expands is therefore not a place, not a medium, not an environment. It is simply the absence of anything, including the absence of space itself. Our language fails us here because all our descriptive words carry spatial connotations. We cannot help but picture something when we hear nothing, even if we understand intellectually that nothing possesses no properties to picture. The universe expands into nothing because there is nowhere else for it to expand. It is the totality of existence, the complete set of all locations and moments. Nothing exists outside because outside is a concept that requires space to have meaning, and all space is within the universe. The balloon trick. Asking what lies outside the universe resembles asking what direction lies north of the North Pole. The question contains a hidden assumption that unravels the moment you examine it closely. At the North Pole, every direction points south. The concept of north loses meaning at that singular point because north is defined relative to the pole itself. Move anywhere from the pole and you're heading south, regardless of which way you turn. The question, what's north of the North Pole, doesn't have an answer because it presumes a framework that doesn't extend beyond that point. The universe presents us with precisely this sort of conceptual boundary, though in a rather more profound sense. The balloon analogy has been deployed by cosmologists for decades, and while it risks becoming rather shop-worn, it genuinely illuminates something essential about cosmic expansion. Take a standard party balloon, preferably one that hasn't been inflated yet, and draw dots across its surface with a marker. These dots represent galaxies. Now inflate the balloon slowly and watch what happens. Every dot moves away from every other dot. The distance between any 2 points increases uniformly. Yet here's the crucial bit. No dot occupies a special position. None sits at the center of the expansion. An observer standing on any dot would see all other dots receding, with more distant dots moving away faster. The surface of the balloon represents the entirety of space in this analogy. Inhabitants living on that surface, restricted to 2 dimensions, would have no awareness of the 3-dimensional room in which the balloon sits. For them, the surface would constitute all of reality. They could measure distances along the surface, map the positions of other dots, and observe the expansion. But they couldn't point outward into the room because outward doesn't exist within their 2-dimensional reality. Their universe, the balloon's surface, would be expanding, yet not expanding into anything they could access or measure. The question, what's outside the balloon, only makes sense from our 3-dimensional perspective, looking at the balloon from outside. For a 2-dimensional being confined to the surface, outside has no meaning. The surface is complete and self-contained. It has no edge, no boundary, no place where you could fall off or encounter a wall. You could travel in any direction and eventually return to your starting point, having circumnavigated the entire universe without ever finding an edge. Our 3-dimensional universe operates similarly. We observe galaxies receding in all directions, with expansion happening uniformly throughout space. General relativity describes this expansion mathematically, without requiring any external dimension. Space itself is the fundamental entity, not something embedded in a larger framework. When we ask, what's outside the universe, we're attempting to apply a spatial concept, outside, to a context where space itself is defined by the universe. The question breaks down because outside presumes a spatial relationship, but all spatial relationships exist within the universe by definition. Einstein's field equations, which form the mathematical foundation of general relativity, treat spacetime as a four-dimensional manifold, 3 dimensions of space and 1 of time. This manifold can curve, stretch, and evolve according to the distribution of matter and energy within it, but it doesn't require embedding in any higher dimensional space. The Friedmann equations, derived from Einstein's work, describe how the universe expands based on its energy content without invoking external dimensions. The North Pole analogy extends further when we consider the beginning of time. Just as there's no direction north of the North Pole, there's no moment before the Big Bang in any conventional sense. Time itself began at the Big Bang, according to general relativity. Asking what happened before involves extending temporal concepts beyond their domain of applicability. Time is a dimension of space-time, and space-time emerged at the universe's beginning. The framework we use to discuss temporal sequences before, after, during, only makes sense within the context of time itself. This philosophical territory feels rather uncomfortable because our intuitions rebel against it. We're accustomed to thinking of everything as existing within something larger. A room exists within a building within a city within a country on a planet within space. The progression seems endless, encouraging us to believe there must always be another layer, another containing structure. But the universe represents the final layer. It's the set of all locations, all moments, all possible positions and times. There is no larger structure containing it because spatial and temporal relationships only exist within it. The balloon trick works not because the universe literally resembles a balloon, but because it demonstrates how expansion can occur without an external medium. The surface of the balloon expands as the balloon inflates, yet the expansion happens entirely within the surface itself from the perspective of any inhabitant. Our universe expands similarly. Distances increase, space grows, yet this growth requires no external space to accommodate it. The question, what's outside, assumes a framework that reality doesn't provide. Like asking what's north of the North Pole, the question itself contains the seeds of its own impossibility. The infinite problem. The universe can be infinite in extent, yet still expand, a statement that sounds like mathematical nonsense until you grasp what expansion actually means in this context. Infinity doesn't work the way our intuitions suggest. Adding to infinity doesn't make it larger in the sense of creating a bigger number, yet space itself can expand even if there's already an infinite amount of it. The resolution lies in understanding that cosmic expansion isn't about adding volume to a fixed container, but about stretching the metric, the fundamental ruler that defines distances. The question, how can something infinite grow larger, assumes that expansion means increasing from one size to another size, the way a balloon grows from deflated to inflated. But infinite space has no size in that sense. It already contains an infinite number of points, an infinite volume. When this infinite space expands, the distances between any 2 points increase, yet the total amount of space remains infinite both before and after. Mathematically, infinity plus infinity equals infinity. The set of points doesn't grow larger, it was already unbounded, but the metric that defines how far apart those points are has changed. To make this concrete, consider an infinite line marked with evenly spaced points, each 1 meter apart. This line extends infinitely in both directions, containing infinitely many points. Now imagine stretching this line so that points which were 1 meter apart are now 2 meters apart. The line is still infinite, it still extends endlessly in both directions, still contains infinitely many points. But the distances between points have doubled. The line has expanded without becoming more infinite, because infinity doesn't admit degrees. You can't have twice as much infinity. Current observations cannot determine whether our universe is spatially infinite or merely extremely large but finite. The observable universe, the spherical region from which light has had time to reach us since the Big Bang, extends roughly 46 billion light-years in every direction. This represents a finite volume simply because light travels at finite speed and the universe has finite age. But the observable universe might be a tiny fraction of the whole. The entire universe could extend infinitely far beyond what we can see, or it could close back on itself in a shape with finite volume but no boundary, like the surface of a sphere. If the universe is infinite, it has been infinite since the Big Bang. The Big Bang did not occur at a point in pre-existing space. Rather, space itself began at the Big Bang, either infinite from the start or finite but expanding. An infinite universe at the moment of the Big Bang would have infinite density everywhere, with every point containing matter and energy at extraordinarily high temperature and pressure. As the universe expanded, this density decreased uniformly throughout all of infinite space. The metric stretched, increasing distances between any 2 points, while the density of matter and energy dropped as the same amount of matter and energy occupied more volume. The mathematics describing this uses the scale factor, a quantity that appears in the Friedmann equations. The scale factor tells us how the metric of space changes over time. When the scale factor doubles, all distances double. In an infinite universe, doubling all distances still leaves you with infinite space, but every specific pair of objects finds itself twice as far apart as before. The scale factor can increase without bound as time progresses, meaning the expansion continues indefinitely, yet if space is infinite, it remains infinite throughout this process. General relativity permits several different geometric possibilities for the universe's global shape. Space might be flat, extending infinitely in all directions like an infinite plane. It might be positively curved, closing back on itself, like a 4-dimensional sphere, finite in volume but with no edge. Or it might be negatively curved, like a saddle extending infinitely with peculiar geometric properties. Current measurements of the cosmic microwave background radiation suggest space is very close to flat, possibly exactly flat, which would imply an infinite universe. But the measurements have finite precision, leaving the possibility of slight curvature and thus finite volume. An infinite universe presents peculiar implications. If space is truly infinite and matter is distributed roughly uniformly beyond what we can observe, then somewhere infinitely far away there exists a region identical to our observable universe. The number of possible arrangements of particles within any finite volume is enormous but finite. With infinite space available, every possible arrangement must occur infinitely many times. There would be infinitely many regions identical to ours, infinitely many copies of Earth, infinitely many versions of you. This follows necessarily from the mathematics of infinite space with finite particle arrangements, though it ventures into territory that feels more philosophical than physical. The expansion of infinite space also affects our cosmic future. As dark energy drives accelerated expansion, galaxies not gravitationally bound to us will recede ever faster, eventually crossing beyond the cosmic event horizon. Even in an infinite universe, we will only ever observe a finite portion, the region from which light can reach us. This observable portion changes over time. Some galaxies currently visible will vanish beyond the horizon, while light from previously hidden regions will arrive. But infinity remains infinity. The universe beyond our observation continues expanding, stretching, evolving, yet always remaining infinite in extent. The edge that isn't. The universe has no edge because edges require boundaries, and boundaries require something on the other side, a distinction between inside and outside that simply doesn't apply when you're discussing all of space. This isn't a matter of the edge being too far away to find or hidden beyond our observational limits. There is no edge in principle, not because the universe extends infinitely in all directions, though it might, but because the concept of an edge breaks down when applied to space itself. Edges exist within space. They define where one region ends and another begins. But space as a whole cannot have an edge in this sense, because there is no other region for it to border. The question, what would happen if you traveled to the edge of the universe, contains the same conceptual flaw as asking what's north of the North Pole. It assumes a framework, a boundary you could approach, reach, and potentially cross that doesn't match reality. If you could somehow travel arbitrarily far in any direction, you would never encounter a wall, a barrier, or a place where space simply stops. In a flat, infinite universe, you would continue forever through more space, passing galaxies separated by ever greater distances due to cosmic expansion. In a finite but unbounded universe, you would eventually return to your starting point, having traveled all the way around, much like circumnavigating Earth. General relativity describes several possible global geometries for space, and none of them include edges. In a flat geometry, space extends infinitely in all directions like an infinite sheet. In a closed geometry, space curves back on itself like the surface of a sphere. You could travel in any direction and never reach a boundary, yet the total volume would be finite. In an open geometry, space has negative curvature, extending infinitely, but with distances behaving differently than in flat space. All three geometries share one crucial property. They contain no edges, no boundaries, no places where you could fall off or encounter a cosmic wall. The observable universe does have a boundary of sorts, the cosmic horizon, beyond which we cannot see because light from more distant regions hasn't had time to reach us. But this horizon is an observational limit, not a physical boundary. It represents the limits of our knowledge, not a wall in space. An observer in a distant galaxy would have their own cosmic horizon centered on their location, different from ours. The cosmic horizon is more like the horizon you see when standing on Earth, a circle where sky meets land than an actual edge. You can travel toward the horizon indefinitely without ever reaching it, because it's defined by your viewing position, not by any feature of the landscape. Early cosmologists briefly entertained the idea that the universe might have an actual boundary, a place where space ends. This would require specifying boundary conditions rules for what happens at the edge. Do particles bounce back? Does space simply stop? Does something exist beyond? Each possibility creates more problems than it solves. If particles bounce back, what surface are they bouncing off? If space simply stops, what prevents it from continuing? If something exists beyond, then that something is part of space, and we haven't actually found the edge. The concept becomes incoherent the moment you examine it closely. Einstein's field equations elegantly sidestep these issues by permitting solutions without boundaries. The equations describe how space-time curves in response to matter and energy without requiring edge conditions. The universe can be self-contained, either infinite in extent or finite, but closed back on itself without needing walls or boundaries to define where it stops. This mathematical property matches what we observe. The cosmic microwave background radiation comes to us from all directions equally, showing no preferred direction, no indication of an edge or boundary anywhere in the universe. The topology of space might still hold surprises. Space could be finite but connected in unusual ways, like a three-dimensional version of a Mobius strip or a torus. In such geometries, you could travel in what seems like a straight line and return to your starting point, having wrapped around the universe. These exotic topologies remain consistent with observations if the universe is large enough. The cosmic microwave background places lower limits on how small such a universe could be, but it cannot rule out finite topologies entirely. Even in these more complex geometries, there would be no edge. You might be able to circumnavigate the universe, discovering that space connects back to itself in unexpected ways, but you would never find a place where space ends. The journey would reveal wrapping or twisting in the fabric of space, not boundaries or walls. The universe would remain complete and self-contained, with no external region to border. This edgeless property of space reflects something fundamental about how we understand existence. Space is not a container that things exist within. It is the relational structure that defines where things are relative to each other. Edges, boundaries, and limits are concepts that make sense for objects within space. A table has edges where its surface ends. A room has walls where interior meets exterior. But space itself cannot have edges because edges are spatial relationships, and all spatial relationships exist within space. The universe's lack of boundaries isn't a contingent fact about how far space happens to extend. It's a logical consequence of what space is. The fourth dimension. Our universe might curve through dimensions entirely beyond our perception, bending in ways that would make perfect geometric sense if only we could step outside our three-dimensional prison and look back. A, being confined to a flat plane, cannot visualize what up means. They can deduce its existence through mathematics, observe its effects, measure how their world behaves differently than pure flatness would predict, but they cannot point toward it or imagine it directly. We find ourselves in precisely this situation, living in three spatial dimensions. While general relativity suggests our space curves through a fourth spatial dimension, we can neither see nor directly experience. The mathematics of this curvature appears in Einstein's field equations with elegant precision. Space-time, described as a four-dimensional manifold 3 of space, one of time can possess intrinsic curvature without requiring embedding in any higher dimension. Yet when cosmologists model the universe's global geometry, they often invoke a fourth spatial dimension as a visualization tool. The surface of a sphere provides the clearest analogy. A two-dimensional being living on a sphere's surface would observe their world as curved. Traveling in what feels like a straight line would eventually bring them back to their starting point. The angles of triangles would sum to more than 180 degrees. Yet their curved surface exists perfectly well as an intrinsic geometry without needing the three-dimensional space in which we visualize the sphere sitting. Our three-dimensional space might behave similarly. If space has positive curvature, it closes back on itself like a three-dimensional analog of a sphere's surface, what mathematicians call a three-sphere or hypersphere. This geometry would have finite volume but no boundary. Travel far enough in any direction and you'd return to your starting point, having circumnavigated the entire universe. The journey might take hundreds of billions of light years, far exceeding the observable universe, but it would eventually loop back. This curvature would exist as an intrinsic property of our three-dimensional space. Yet mathematically, it can be visualized as our space curving through a fourth spatial dimension, the way a sphere's surface curves through our familiar three dimensions. General relativity permits three possible geometries for space on the largest scales. Flat space with zero curvature extends infinitely in all directions like an infinite plane. Positively curved space closes back on itself with finite volume. Negatively curved space, like a saddle, extends infinitely, but with peculiar geometric properties. The angles of triangles sum to less than 180 degrees, and parallel lines diverge, rather than remaining equidistant. Current observations of the cosmic microwave background indicate that space is remarkably close to flat, possibly exactly flat, though the measurements cannot rule out slight curvature. If our universe does curve through a fourth dimension, we would observe specific signatures. Light traveling across curved space would take paths that appear bent when mapped onto flat coordinates. The distribution of galaxies would show patterns reflecting the underlying curvature. Most tellingly, the cosmic microwave background radiation, the afterglow of the Big Bang, would display specific patterns in its temperature variations. These patterns depend sensitively on the geometry of space. The Wilkinson Microwave Anisotropy Probe, and later the Planck satellite, measured these patterns with extraordinary precision, finding that space is flat to within less than 1% curvature. The fourth dimension, if it exists as more than mathematical convenience, would represent a direction fundamentally inaccessible to us. We cannot point toward it. We cannot move through it. Our particles, our forces, our light, all confined to three-dimensional space, cannot access this perpendicular direction. Yet, our space might still curve through it, bending in ways that affect how distances work, how geodesics behave, how the universe's total volume relates to its observable properties. Higher dimensional theories in physics sometimes invoke additional spatial dimensions beyond the fourth. String theory, for instance, requires 9 or 10 spatial dimensions for mathematical consistency. These extra dimensions, according to the theory, are compactified, curled up into tiny spaces far smaller than atomic nuclei, so small that we cannot detect them directly. Our three familiar dimensions extend across the observable universe, while the others remain microscopic. But the fourth spatial dimension relevant to cosmic curvature operates differently. If it exists, it provides the direction through which our entire three-dimensional space bends. The concept challenges visualization precisely because our brains evolved to navigate three spatial dimensions. We can imagine a two-dimensional surface curving through our three-dimensional world easily. We see it constantly in everyday objects. But envisioning our three-dimensional space curving through a fourth dimension exceeds our intuitive capacity. We can work with it mathematically, describe it precisely in equations, make predictions about what we should observe if such curvature exists. We can even build physical models that capture aspects of the geometry. But we cannot picture it directly any more than a flatland inhabitant could picture a sphere. This limitation highlights something profound about how we understand the cosmos. Our theories transcend our ability to visualize them. We construct mathematical frameworks that describe reality with stunning accuracy despite describing phenomena we cannot directly imagine. The fourth dimension, whether it exists as a real geometric feature or merely as a mathematical tool, demonstrates that understanding need not require visualization. The universe might curve in ways our minds cannot picture, yet we can still map that curvature, measure it, predict its consequences, and test those predictions against observation. The stretching proof. Light traveling across billions of light years of expanding space arrives at our telescopes stretched, its wavelengths elongated by the growth of space itself during the photon's journey, providing the most direct evidence we possess that cosmic expansion involves the fabric of space rather than mere motion through space. This stretching manifests as redshift, a shift of light toward longer, redder wavelengths, and it operates through a mechanism fundamentally different from the Doppler effect, though the two are often confused. The distinction matters because it reveals what expansion actually is. The Doppler effect occurs when a source moves through space toward or away from an observer. An approaching ambulance's siren sounds higher pitched because successive sound waves are compressed, emitted from positions progressively closer to your ear. A receding ambulance sounds lower pitched as successive waves are stretched, emitted from positions progressively farther away. Light exhibits the same behavior. A star moving toward Earth shows blue shift compressed wavelengths, while a star moving away shows redshift. But the Doppler effect assumes motion through a static medium. The source moves. The space between source and observer remains fixed. Cosmological redshift operates differently. The galaxies emitting the light we observe are not, strictly speaking, moving through space at all, at least not at the tremendous velocities their redshifts would suggest. They sit relatively still within their local patch of space-time, perhaps drifting slightly due to gravitational influences, but not racing through the cosmos at speeds approaching or exceeding light. Instead, space itself expands between the galaxy and our telescopes. A photon emitted from a distant galaxy begins its journey with some particular wavelength determined by the atomic transition that produced it. As this photon travels through space, space itself stretches. The photon's wavelength stretches along with space, growing longer in proportion to how much space has expanded during the journey. Edwin Hubble discovered this effect in 1929 when he measured the distances and velocities of galaxies. Using Cepheid variable stars as distance indicators, he established how far various galaxies lay from Earth. Using spectroscopy, he measured how much their light had been redshifted. The pattern was unmistakable. More distant galaxies showed greater redshift. The relationship between distance and redshift followed a linear pattern, suggesting a universe expanding uniformly in all directions. Hubble's law, as it came to be known, relates recession velocity to distance through the Hubble constant. This relationship only makes sense if space itself expands, carrying galaxies along while stretching the light traveling between them. The spectrum of light from distant galaxies provides detailed confirmation. Atoms emit and absorb light at specific wavelengths, creating characteristic patterns of spectral lines. Hydrogen, for instance, produces a series of lines at precise wavelengths when its electrons transition between energy levels. These wavelengths are determined by fundamental physics and remain constant. When we observe light from a distant galaxy, we see these same spectral lines, but shifted uniformly toward longer wavelengths. The entire spectrum stretches by the same proportion. If the galaxy were simply moving through space, we would observe a Doppler shift, but various emission mechanisms might show different shift patterns. The uniform stretching of all wavelengths indicates that space itself has expanded. The degree of stretching tells us how much the universe has expanded since the light was emitted. Astronomers quantify this using redshift parameter Z, defined so that a redshift of 1 means wavelengths have doubled. A galaxy with redshift 2 shows wavelengths stretched to 3 times their original length, indicating the universe has expanded by a factor of 3 since that light was emitted. The most distant galaxies observed have redshifts exceeding 11, meaning the universe has expanded more than 12-fold since their light began traveling toward us. These galaxies emitted their light when the universe was less than 500 million years old in its early formative period. The stretching affects all electromagnetic radiation identically. Radio waves, infrared, visible light, ultraviolet, X-rays all get stretched by exactly the same proportion during their journey through expanding space. This universality confirms that the expansion involves the metric of space itself. The wavelength of light is fundamentally a spatial measurement, the distance between successive wave crests. When space expands, all spatial measurements increase proportionally, including wavelengths. This stretching also explains why the cosmic microwave background radiation appears as it does. This radiation, emitted roughly 380,000 years after the Big Bang, emerged as visible and ultraviolet light when atoms first formed and the universe became transparent. The photons from this epoch have been traveling through space for nearly 13.8 billion years. During that time, the universe has expanded by a factor of roughly 1,100. The originally visible light has been stretched into microwaves, with wavelengths roughly 1,100 times longer than when emitted. We detect this radiation coming from all directions, uniformly filling the sky, its spectrum precisely matching that of a black body at 2.7 degrees above absolute zero, the temperature you'd expect from such extreme stretching. The stretching even affects the energy of photons. Energy and wavelength relate inversely. Longer wavelengths mean lower energy. As space expands and stretches light to longer wavelengths, the energy of that light decreases. This energy doesn't vanish. It gets diluted across the expanding volume of space. The universe as a whole cools as it expands, not because heat flows away to some external reservoir, but because expansion reduces the energy density of radiation uniformly throughout all of space. The stretching of light thus provides multiple converging lines of evidence that expansion involves space itself. The uniform stretching of all wavelengths, the precise relationship between distance and redshift, the cooling of radiation across cosmic time, and the appearance of the cosmic microwave background all point to the same conclusion. Space grows, carrying everything within it along, stretching the very fabric through which light propagates. The dark push. Empty space pushes outward with a force that grows stronger as the universe expands, a phenomenon so counterintuitive that when Einstein first encountered it in his equations, he added a term specifically to make it go away, only to have observations decades later reveal he'd been right to include it. This force, now called dark energy, accounts for roughly 68% of the universe's total energy content. Yet it manifests through no particles we can detect, generates no heat, emits no light, and interacts with matter only through gravity. It simply fills space uniformly, exerting a repulsive gravitational effect that accelerates cosmic expansion. The discovery came in 1998 when two independent teams studying distant supernovae found results nobody expected. Type Ia supernovae serve as excellent standard candles because they occur when white dwarf stars accumulate enough mass to trigger runaway fusion, producing explosions of remarkably consistent brightness. By measuring how bright these supernovae appear from Earth and comparing that to their known intrinsic brightness, astronomers can calculate their distances with good precision. Both research teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, were using this technique to measure the universe's expansion history. The expectation was straightforward. The universe began expanding at the Big Bang. Gravity, being an attractive force, should slow this expansion over time. Depending on how much matter the universe contains, expansion might slow enough to eventually reverse into contraction, or it might continue forever, but at an ever-decreasing rate. Either way, the expansion should be slowing down. Distant supernovae, whose light shows us what the universe was like billions of years ago, should reveal a younger universe expanding faster than today. The observations showed the opposite. Distant supernovae appeared dimmer than expected, indicating they were farther away than they should be if expansion were slowing. The only way to explain this was if expansion has been speeding up. Galaxies that were already receding are receding faster now than they were billions of years ago. The expansion rate is increasing, driven by something that acts like a repulsive form of gravity, pushing space apart with ever greater vigor. This acceleration requires something with very peculiar properties. Normal matter and energy dilute as the universe expands. If you have a certain amount of mass in some volume of space, and that volume doubles due to expansion, the density of mass drops by half. Radiation dilutes even faster because expansion also stretches wavelengths, reducing energy. But dark energy behaves differently. It maintains constant density as space expands. Create twice as much space, and you create twice as much dark energy. This property means dark energy's influence grows over time as the universe expands, while the influence of matter and radiation diminishes. The mathematics of general relativity permits this through the cosmological constant, a term Einstein introduced in 1917. At that time, the prevailing view held that the universe was static, neither expanding nor contracting. Einstein's equations, however, predicted that a universe filled with matter would collapse under its own gravity. To prevent this, he added the cosmological constant, a term representing a uniform energy density filling all of space, exerting repulsive gravity just strong enough to balance matter's attractive gravity. When Hubble discovered cosmic expansion in 1929, a static universe became unnecessary, and Einstein famously called the cosmological constant his biggest blunder, removing it from his equations. But the cosmological constant refused to stay removed. Quantum field theory predicts that empty space should possess energy even in its lowest energy state. Virtual particles continuously pop into and out of existence, borrowing energy from the vacuum for infinitesimally brief moments. These quantum fluctuations contribute to what physicists call vacuum energy. The calculations attempting to estimate this vacuum energy's magnitude produce famously absurd results, predictions exceeding observed values by more than 120 orders of magnitude, the worst prediction in the history of physics. Yet despite this theoretical embarrassment, observations indicate that something very much like a cosmological constant fills the universe. Dark energy, if it is indeed vacuum energy, exerts negative pressure. Pressure normally pushes outward from high-density regions toward low-density regions, but vacuum energy is perfectly uniform, so its pressure has nowhere to push. Instead, this pressure couples to gravity in a peculiar way. Einstein's equations link energy density and pressure to space-time curvature. Positive pressure contributes to attractive gravity. Negative pressure contributes to repulsive gravity. Vacuum energy has negative pressure in just the right proportion, 3 times its energy density, but opposite in sign, to produce net repulsive gravity that exactly balances the attractive gravity from its energy density, leaving pure cosmic acceleration. The effect grows with time. In the universe's early history, matter and radiation dominated. Their densities were high enough that dark energy, though present, contributed negligibly to cosmic dynamics. As the universe expanded, matter and radiation diluted, while dark energy maintained constant density. Eventually, around 5 billion years ago, dark energy began dominating. From that point forward, expansion started accelerating rather than slowing. The transition is visible in observations of supernovae at different distances nearby. Supernovae show acceleration, while very distant ones, showing the universe as it was before dark energy dominated, show deceleration. This acceleration has profound implications for the cosmic future. As expansion continues and accelerates, galaxies not gravitationally bound to our local group will recede faster and faster, eventually crossing beyond the cosmic event horizon, where space between us expands faster than light can traverse it. The observable universe will shrink not in absolute size, but in how much of the total universe we can observe. Within roughly 150 billion years, an observer in our galaxy would see only the local group, the Milky Way, Andromeda, and associated dwarf galaxies, all merged into a single large galaxy. Beyond that, only empty, expanding space. Dark energy remains deeply mysterious. We observe its effects clearly. The accelerating expansion leaves unmistakable signatures in multiple, independent measurements. But we have no fundamental understanding of what it is. If it's vacuum energy, why does its measured density differ so catastrophically from quantum field theory predictions? If it's not vacuum energy, what is it? Could it be a new field pervading space, distinct from known quantum fields? Might it vary in strength over time or space rather than remaining constant? These questions remain unanswered, representing one of the deepest mysteries in contemporary physics. The nothing between galaxies is filled with something we cannot see, cannot touch, cannot comprehend, yet which dominates the universe's fate and drives it toward an ever faster expansion into an even emptier future. The quantum nothing. Empty space seethes with activity at scales far below anything we can observe directly. A quantum restlessness where particle pairs materialize from pure vacuum, exist for impossibly brief moments, then annihilate back into nothingness, leaving behind measurable effects that prove this apparent void possesses genuine physical properties: weight, pressure, energy density. The vacuum is not empty. It cannot be empty, because quantum mechanics forbids true emptiness. Uncertainty principles prevent any region of space from settling into a perfectly quiescent state. Even in the absence of matter, radiation, or any conventional form of energy, quantum fields pervade all of space, fluctuating in their ground states, creating transient particles that challenge our classical intuitions about what nothing means. These virtual particles emerge in pairs: an electron and its antimatter counterpart, a positron, or a quark and antiquark, or photons appearing in pairs that satisfy conservation laws. They borrow energy from the vacuum itself, permitted by Heisenberg's uncertainty principle, which allows brief violations of energy conservation on timescales inversely proportional to the energy borrowed. A particle pair with mass equivalent to 1 electron volt can exist for roughly 6.6 times 10 to the minus 16th seconds. Heavier particles require more energy and thus persist for even briefer intervals. These particles cannot persist long enough to be detected directly, yet their existence produces observable consequences. The Casimir effect demonstrates this quantum vacuum activity with elegant simplicity. Two uncharged metal plates placed extraordinarily close together in a vacuum experience. A measurable, attractive force pushing them together. The explanation lies in how the plates constrain quantum fluctuations. Between the plates, only virtual photons with wavelengths that fit precisely into the gap can exist, standing waves with nodes at both plates. Outside the plates, virtual photons of all wavelengths materialize and vanish freely. This creates an imbalance in radiation pressure. Fewer virtual photons exist between the plates than outside them, producing a net force pushing the plates together. Dutch physicist Hendrik Casimir predicted this effect in 1948, and subsequent experiments confirmed it with precision, measuring forces of mere billionths of a Newton on plates separated by micrometers. The vacuum energy arising from these quantum fluctuations contributes to what cosmologists observe as dark energy. Quantum field theory predicts that empty space should possess energy even in its lowest possible state. Every quantum field, electromagnetic, electron, quark, and others, contributes fluctuations to the vacuum. Calculating the total vacuum energy by summing contributions from all possible wavelengths produces an absurdly large number, more than 120 orders of magnitude greater than what observations indicate. This discrepancy, the cosmological constant problem, represents perhaps the worst prediction in physics history, suggesting our understanding of quantum vacuum energy remains profoundly incomplete. Yet despite this theoretical embarrassment, observations confirm that vacuum energy exists and affects cosmic expansion. The measured density of dark energy, roughly 6 times 10 to the minus 10th joules per cubic meter, matches what would be expected from a cosmological constant, a uniform energy density filling all of space. This energy exerts negative pressure, a property that sounds peculiar but emerges naturally from quantum field theory. Pressure normally represents force per unit area from particles bouncing off boundaries, but vacuum energy fills space uniformly with nothing to bounce off. Instead, Its pressure couples to gravity in Einstein's equations, and negative pressure produces repulsive gravitational effects. The quantum nothing thus possesses weight in the sense that energy and mass are equivalent through Einstein's famous relation. Every cubic meter of empty space contains energy, and that energy gravitates, influencing how space-time curves and how the universe expands. The pressure of this vacuum energy, 3 times its energy density but opposite in sign, contributes to gravity in a way that produces net cosmic repulsion. The combination drives accelerating expansion, with empty space pushing itself apart through its own quantum properties. Virtual particles also affect how real particles behave. Electrons moving through vacuum interact with the fleeting virtual particle pairs surrounding them, slightly altering the electron's observed mass and charge. These quantum electrodynamic effects have been calculated and measured to extraordinary precision, with theory and experiment agreeing to better than 1 part in a trillion. The vacuum participates actively in particle physics, not as passive emptiness, but as a dynamic medium influencing everything passing through it. This quantum restlessness extends throughout the universe. Every cubic centimeter of intergalactic space, every region between stars, every gap between atoms, all filled with fluctuating quantum fields. The nothing between galaxies is as full of quantum activity as the nothing in this room, though vastly more of it exists due to cosmic expansion. As the universe expands and creates more space, it creates more vacuum energy, since vacuum energy maintains constant density. This property distinguishes it from matter and radiation, which dilute as space grows. The quantum nothing multiplies as expansion proceeds, and its repulsive gravity accelerates that expansion in a runaway process that appears destined to continue indefinitely. The first moment. The universe emerged from a state so impossibly small and dense that our physics breaks down when attempting to describe it. A singularity where all of space and time compressed into a region smaller than an atom, perhaps infinitely small, containing all the energy that would eventually become the observable universe and everything beyond. This was not an explosion into pre-existing space, but the appearance of space itself, along with time, matter, energy, and all physical laws. The Big Bang happened everywhere simultaneously, because everywhere existed in that tiny hot beginning. There was no outside, no before, no location where it occurred. It simply was the start of everything we can measure or observe. The first fraction of a second saw changes so rapid and profound that describing them requires conditions we cannot recreate or fully test. At 1 Planck time, after the beginning, roughly 5.4 times 10 to the minus 44 seconds, the universe had cooled enough that quantum mechanics and general relativity might begin to apply separately. Though we lack a unified theory to describe their interplay at this earliest instant, temperature exceeded 10 to the 32 degrees Kelvin. Density exceeded 10 to the 96 kilograms per cubic meter. The 4 fundamental forces, gravity, electromagnetism, strong nuclear force, weak nuclear force, may have been unified into a single force, though this remains speculative. Within the first trillionth of a second, cosmic inflation likely occurred, a period when space expanded at a truly staggering rate. The inflationary hypothesis, proposed by Alan Guth in 1980, suggests that a peculiar quantum field filled the early universe, stuck in a high-energy state that acted like a cosmological constant. This field's energy drove exponential expansion. In less than 10 to the minus 32 seconds, the universe's scale could have increased by a factor exceeding 10 to the 26, transforming a region smaller than a proton into something potentially larger than a grapefruit. This expansion happened faster than light could travel, not violating relativity because space itself expanded rather than matter moving through space. Inflation solved several puzzles. It explained why the universe appears so uniform in all directions, distant regions that now seem too far apart to have ever interacted were actually close together before inflation stretched them apart. It explained why space appears flat rather than curved. Any initial curvature would have been stretched smooth, like wrinkles on a rapidly inflated balloon. It explained why we don't observe magnetic monopoles or other exotic particles predicted to form in the earliest moments. Inflation diluted them to undetectable densities. When inflation ended, the energy stored in the inflaton field converted into ordinary matter and radiation through a process called reheating. The universe transformed from a cold, empty state dominated by the inflaton's energy to a hot, dense plasma filled with elementary particles. Temperature spiked to perhaps 10 to the 27 degrees Kelvin. Quarks, leptons, photons, and other particles filled space at extraordinary densities, interacting furiously as the universe continued expanding, though now at a more sedate rate compared to inflation. By 1 microsecond after the Big Bang, the universe had cooled enough for quarks to combine into protons and neutrons. The strong nuclear force, which binds quarks together, operates only over extremely short distances, requiring quarks to be confined within about 10 to the minus 15 meters. When the universe was hotter and denser, thermal energies exceeded the binding energies of protons and neutrons, keeping quarks free. As temperature dropped below roughly 10 trillion degrees, quarks combined permanently into composite particles. This transition, called the quark-hadron transition, produced the protons and neutrons that would eventually form atomic nuclei. Between 1 and 3 minutes after the beginning, Big Bang nucleosynthesis occurred. Temperatures had fallen to roughly 1 billion degrees Kelvin, cool enough for protons and neutrons to stick together when they collided, forming deuterium nuclei, 1 proton bound to 1 neutron. These deuterium nuclei could capture additional protons or neutrons, building up helium nuclei and trace amounts of lithium. The proportions matched what nuclear physics predicted, roughly 75% hydrogen, 25% helium by mass, with tiny amounts of heavier elements. These predictions match observations of the oldest stars and gas clouds with remarkable precision, providing strong confirmation of the Big Bang model. For the next 380,000 years, the universe remained opaque, a glowing plasma where electrons, protons, and photons interacted constantly. Light could not travel freely because photons scattered off free electrons every few centimeters, creating a thick fog. But as the universe expanded and cooled, eventually temperatures dropped to roughly 3,000 degrees Kelvin, cool enough for electrons and protons to combine into neutral hydrogen atoms. This recombination decoupled photons from matter. Light could suddenly stream freely across space without scattering. The universe became transparent. Those photons have been traveling through space ever since, stretched by cosmic expansion from visible light into microwaves, the cosmic microwave background we observe today. From this impossibly small beginning, through inflation, nucleosynthesis, and recombination, the universe expanded into the vast structure we observe. Galaxies formed from tiny density fluctuations imprinted during inflation. Stars ignited, planets coalesced, and eventually, on at least one world, life emerged capable of looking back toward those first moments and attempting to understand them. The universe exploded from nothing into everything, and that process continues still, with space expanding, carrying galaxies apart, creating more nothing filled with quantum energy that drives ever faster expansion. The runaway expansion. Expansion accelerates with distance in a process that feeds on itself, where more space means more dark energy, means faster expansion, means more space being created. A cycle that grows more extreme the farther you look and appears destined to continue indefinitely into a cold, dark future. This runaway quality, emerges directly from dark energy's peculiar property of maintaining constant density as space expands. Unlike matter or radiation, which become diluted as the universe grows, dark energy's density remains fixed. Each cubic meter of new space contains the same amount of dark energy as every existing cubic meter, and since dark energy drives expansion through its repulsive gravity, creating more space creates more of the very thing that causes space to expand. The relationship between distance and expansion velocity follows Hubble's law. Galaxies separated by greater distances recede from each other faster than nearby galaxies. This linear relationship means that recession velocity increases proportionally with distance double the distance, and you double the recession rate. The Hubble constant describes this relationship, currently measured at roughly 70 kilometers per second per megaparsec. A galaxy 1 megaparsec away, about 3.26 million light-years, recedes at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. A galaxy 1,000 megaparsecs distant recedes at 70,000 kilometers per second. This pattern holds because expansion happens uniformly throughout space. Every megaparsec of distance contributes the same amount to recession velocity. When you look at a galaxy 1 billion light-years away, there's a billion light-years of expanding space between you and that galaxy. Each small volume of that space expands by a tiny amount, but with a billion light-years worth of small volumes, all those tiny expansions add up to substantial recession velocity. The farther the galaxy, the more intervening space, the faster the recession. At sufficiently large distances, the cumulative expansion of all that intervening space produces recession velocities exceeding the speed of light. Dark energy amplifies this effect over time. In the universe's early history, when matter and radiation were much denser than today, their gravitational influence dominated cosmic dynamics. Expansion occurred but decelerated, slowing down gradually as matter's gravity pulled back against it. Dark energy existed then, but at the same density it has now, which was negligible compared to the energy density in matter and radiation. As the universe expanded, matter and radiation diluted while dark energy maintained constant density. Eventually, around 5 billion years ago, dark energy's density surpassed matter's density, and its repulsive gravity began dominating cosmic dynamics. From that transition point forward, expansion started accelerating rather than decelerating. The acceleration appears modest when measured over human timescales, roughly 1% faster every 140 million years. But cosmic timescales extend across billions of years, and over such durations, even modest acceleration compounds dramatically. A galaxy, currently 1 billion light-years away, will be farther in the future, receding faster due to both the original expansion and the additional acceleration from dark energy. That galaxy's increased distance means more intervening space, which means even more dark energy contributing to the expansion between us. The runaway nature becomes clear when you trace this forward. As the universe expands, distances grow. Growing distances mean more total dark energy, since its density stays constant. More dark energy means stronger repulsive gravity. Stronger repulsive gravity accelerates expansion further. Faster expansion creates new space more quickly. More new space means yet more dark energy. The cycle reinforces itself without limit, driving expansion ever faster. This creates the cosmic event horizon, a distance beyond which galaxies recede faster than light can traverse the expanding space between us and them. This horizon exists at roughly 16 billion light-years currently. Galaxies beyond this distance are receding so rapidly that light, leaving them now, traveling toward us at light speed, can never close the gap. The expansion of intervening space adds distance faster than the photon can cross it. The photon swims upstream against a current that exceeds its swimming speed, making progress but never enough to reach us. As expansion accelerates, this cosmic event horizon draws closer in terms of which galaxies cross it. Galaxies currently within the horizon will eventually cross beyond it as accelerating expansion carries them away faster. Any light they emit after crossing becomes permanently unable to reach us. We can still see these galaxies for billions of years afterward because we're observing old light emitted before they cross the horizon, but they're effectively disconnected from our causal future. We cannot signal them, visit them, or exchange information with them. They've slipped beyond reach, carried away by the multiplication of dark energy-filled space. Observational evidence for this acceleration comes from multiple sources that converge on the same picture. Type Ia supernovae at varying distances show how expansion rate has changed over time. The cosmic microwave background radiation's detailed patterns reveal the universe's energy content and geometry. Large-scale surveys mapping galaxy distributions confirm how structure has evolved under accelerating expansion. Baryon acoustic oscillations, subtle patterns in galaxy clustering, provide another distance measurement independent of supernovae. All these observations agree. The universe's expansion is accelerating, driven by dark energy that constitutes roughly 68% of the total energy budget. The multiplication of nothing thus determines cosmic fate. As expansion continues, galaxies not bound to us by gravity will vanish beyond the horizon. Within 150 billion years, an observer in our galaxy would see only the local group, our merged local galaxies, forming a single, large elliptical galaxy surrounded by empty space. The cosmic microwave background would have redshifted into undetectability. No external galaxies would remain visible. An astronomer in that distant epoch, unaware of our current observations, might conclude the universe consists of a single galaxy surrounded by infinite empty space with no evidence of the Big Bang or cosmic expansion. The runaway expansion would have carried away all the evidence, leaving future civilizations isolated in their island of matter, surrounded by an accelerating ocean of expanding nothingness. The lost universe. 95% of all galaxies in the universe have already slipped beyond our cosmic event horizon, carried away by accelerating expansion into regions from which their light can never reach us, making them permanently invisible and forever inaccessible, regardless of how advanced our technology becomes. We're observing a universe already in the process of vanishing, watching ancient light from galaxies that crossed this boundary billions of years ago, their present state hidden from us by the insurmountable barrier of faster-than-light expansion. The observable universe, the sphere of space from which light has had time to reach us since the Big Bang, represents only a tiny fraction of what exists. Everything beyond lies in a realm we can never visit, never observe, never influence. The cosmic event horizon works differently than the one surrounding a black hole, yet produces similarly absolute separation. With a black hole, matter falls inward past a boundary where escape velocity exceeds light speed. With the cosmic horizon, space expands outward so rapidly that light cannot traverse it. A galaxy currently sitting at the horizon emits photons toward us, and those photons travel at light speed through their local space, making genuine progress toward Earth. But the space between that galaxy and us expands faster than the photon can cross it. The photon swims forward while the finish line recedes faster than it can swim. It moves but never arrives. This boundary exists at roughly 16 billion light-years from Earth currently, though the exact distance depends on how we define it and which cosmological parameters we use. Galaxies beyond this distance recede faster than light due to the cumulative expansion of all the intervening space. Their light, emitted now or at any point in the future, cannot reach us. We're causally disconnected from these regions. Any signal we might send, electromagnetic, gravitational, or otherwise, would similarly fail to bridge the gap. The expansion creates an impenetrable barrier, not because of any physical wall, but because of geometry itself. We can still observe many galaxies beyond the current horizon because we're seeing old light they emitted billions of years ago when they were closer and hadn't yet crossed the boundary. The light from a galaxy now 20 billion light-years away might have been emitted when that galaxy was only 10 billion light-years distant, at a time when the expansion rate was slower and the cosmic horizon farther out. That ancient light has spent billions of years traveling toward us, crossing through expanding space, its wavelength stretched to longer values, but eventually arriving at our telescopes. The galaxy we observe no longer exists in that state. It has evolved, changed, perhaps merged with other galaxies, but we cannot know because no information about its current state can reach us. The fraction of unreachable galaxies continues growing. As dark energy drives accelerated expansion, the cosmic horizon draws closer in terms of which galaxies lie beyond it. Galaxies currently within 16 billion light-years will eventually cross beyond it as expansion carries them away faster. Light they emit after crossing becomes permanently unable to reach us, though we'll continue seeing progressively older light they emitted before crossing for billions of years afterward. The observable universe's edge, the most distant observable galaxies, lies much farther than the cosmic horizon, currently at roughly 46 billion light-years, because we observe light from when those regions were much closer. But this observational limit also represents galaxies whose current state we can never know. Calculating the fraction of unreachable galaxies requires estimating the total number of galaxies in the universe beyond what we can observe. The observable universe contains roughly 200 billion to 2 trillion galaxies, depending on how we count small, faint systems. But if the universe extends infinitely beyond what we observe, the total number would be infinite, making the fraction of unreachable galaxies approach 100%. Even if the universe has finite volume but extends far beyond our observable horizon, the fraction of galaxies we can access remains extremely small. Current estimates suggest that approximately 95% of galaxies in the total universe observable and unobservable combined have already crossed beyond our cosmic event horizon. We can see perhaps 5% of all galaxies that exist, and that fraction decreases as expansion continues. Within the observable universe, a somewhat larger fraction remains accessible because we're including galaxies whose ancient light reaches us even though their current state lies beyond the horizon. But in terms of galaxies we could potentially visit, signal, or learn about in their present state, the vast majority have vanished. This loss represents more than mere distance. These galaxies contain stars, planets, potentially civilizations. If life arose on worlds orbiting stars in those galaxies, we can never know. If intelligence evolved there, developed technology, built cities, asked questions about the cosmos, we remain forever ignorant. They exist in a universe causally disconnected from ours. Their light trapped on the wrong side of an expanding barrier we can neither cross nor see through. The information they contain, their histories, their discoveries, their very existence has been deleted from our accessible universe, carried away by the relentless multiplication of space. The realization that we've already lost contact with most of the universe carries a certain melancholy. The cosmos appears vast when we observe billions of galaxies through our telescopes, yet this vastness represents only a remnant of what exists. The true universe extends far beyond, populated by structures we can never observe, governed by the same physical laws but forever isolated from our knowledge. Expansion has already stolen most of reality from our view, and it continues stealing more with each passing moment, a cosmic forgetting that erases increasing fractions of existence from our possible experience. The lonely future. Trillions of years from now, An astronomer in our galaxy would look up at a night sky emptied of all external galaxies, seeing only the stars of their own merged local group against an utterly black background. With no cosmic microwave background, no distant galaxies, no evidence that the universe extends beyond their isolated island of matter surrounded by infinite expanding emptiness. This is not speculation or uncertain prediction, but the inevitable consequence of accelerating expansion driven by dark energy. The universe we observe, rich with galaxies and structure, represents a brief epoch in cosmic history. The far future promises isolation and darkness as expansion carries away everything not gravitationally bound to us. The local group, our gravitational neighborhood containing the Milky Way, Andromeda, Triangulum, and roughly 50 smaller galaxies, will merge into a single, large elliptical galaxy within several billion years. Gravity holds these galaxies together tightly enough to overcome cosmic expansion. While space expands uniformly on large scales, local regions where gravity dominates remain bound. Our local group represents such a region. As member galaxies orbit each other, gravitational interactions will eventually cause them to merge, a process already underway. The Milky Way and Andromeda are approaching each other at roughly 120 kilometers per second and will collide in about 4 billion years, beginning a merger that will take several billion years to complete. Meanwhile, every galaxy outside our local group recedes, carried away by expansion. The nearest large galaxy cluster, the Virgo cluster, sits roughly 65 million light-years away currently. Its galaxies recede at roughly 1,200 kilometers per second. Over billions of years, this recession will accelerate as dark energy increasingly dominates cosmic dynamics. Eventually, Virgo's galaxies will cross our cosmic event horizon, vanishing from view. Their light will redshift to longer and longer wavelengths, dimming and fading until the last photons arrive, and then nothing more. Every galaxy cluster beyond our local group will follow the same trajectory. Coma, Fornax, Perseus, all the great clusters visible in our current sky will fade and disappear as accelerating expansion carries them beyond reach. The process occurs gradually, taking billions of years, but it's inexorable. Within roughly 150 billion years, every external galaxy will have vanished. An observer in that distant future would see only their own merged galaxy, perhaps labeled something like Milkomeda, or simply the galaxy, floating in an ocean of empty space. The cosmic microwave background radiation will also disappear. This faint glow currently fills the entire sky at microwave wavelengths, the stretched remnant of light from the early universe. As expansion continues, this radiation gets stretched to ever longer wavelengths. Currently at microwave frequencies, it will shift into radio waves, then to longer and longer wavelengths, becoming progressively more difficult to detect. The photons become increasingly spread out, their energy diluted across expanding space. Within a few trillion years, the cosmic microwave background will have redshifted beyond any possibility of detection, its photons stretched to wavelengths longer than the observable universe. The night sky in this far future would appear utterly different from ours. Instead of thousands of visible stars and billions of galaxies detectable through telescopes, observers would see only the stars of their own galaxy. No external galaxies, no galaxy clusters, no cosmic web of structure, just their island of stars surrounded by perfect blackness, extending infinitely in all directions. If these future astronomers didn't have records from our epoch, they might conclude the universe consists solely of their galaxy, surrounded by infinite empty space. Such astronomers would face profound difficulties reconstructing cosmic history. The Big Bang theory relies heavily on observations of galactic redshifts, the cosmic microwave background, and the distribution of galaxies across space. Without these observables, determining that the universe began in a hot, dense state, that space expands, that dark energy exists, all these discoveries would become nearly impossible. The evidence would have vanished, carried away by the very expansion it once revealed. Stars in the merged galaxy would continue shining for trillions of years, but eventually stellar formation would cease as hydrogen supplies dwindle. Existing stars would gradually exhaust their fuel, leaving behind white dwarfs, neutron stars, and black holes. The galaxy would fade from a bright spiral or elliptical to a dim collection of stellar remnants. After perhaps 100 trillion years, star formation would effectively end throughout the galaxy. After 1 quadrillion years, even the longest-lived red dwarf stars would burn out. The galaxy would go dark. In this desolate future, separated by unimaginable spans of time from our epoch, the universe would have transformed from rich structure spanning billions of light years into isolated islands of dead stars separated by exponentially expanding voids of space. Any intelligence surviving in such an era would inherit a cosmos unrecognizable compared to ours, dark, cold, and profoundly lonely. The expansion that shapes our universe today, currently creating beautiful cosmic structure and fueling stellar nurseries, will ultimately erase that structure and leave only isolated remnants floating in an expanding void. The timescales involve dwarf human comprehension. Trillions of years exceed the current age of the universe by factors of thousands. Yet physics permits us to extrapolate forward, applying what we know about dark energy, stellar evolution, and cosmic expansion to sketch this distant future. The universe we observe represents a fleeting moment of richness and connectivity. The overwhelming majority of cosmic time will be spent in the dark, empty, lonely state that awaits. Expansion into nothing will ultimately leave behind almost nothing scattered islands of dead matter in an infinite ocean of space, eternally alone. The creation paradox. Something emerged from nothing at the universe's beginning, a statement that sounds like philosophical nonsense or theological claim, yet describes what cosmology and quantum mechanics together suggest actually happened. With the expansion of space itself providing the mechanism through which nothing became everything without violating conservation of energy. The paradox dissolves when we recognize that gravitational energy can be negative, balancing the positive energy of matter and radiation, potentially allowing the total energy of the universe to be exactly zero. The universe might be the ultimate free lunch, a vast cosmos containing stupendous quantities of energy arising from a quantum fluctuation in which total energy remained zero throughout. The puzzle appears stark when stated plainly. Energy cannot be created or destroyed according to fundamental physical laws. Yet the universe contains energy in matter, radiation, dark energy, and the motion of objects. Where did this energy come from? If the universe began at the Big Bang, as observations strongly suggest, how did all this energy appear? The answer requires understanding both how gravity works and how quantum mechanics operates at the most fundamental levels. Gravity differs from other forces in a crucial way. While electromagnetic forces, nuclear forces, and other interactions involve positive energy, gravitational potential energy is negative. When two masses attract each other and move closer together, they lose potential energy, which gets converted into kinetic energy or radiation. The closer they get, the more negative the gravitational potential energy becomes. For the universe as a whole, all the matter pulling on all other matter creates enormous negative gravitational potential energy. This negative energy might precisely balance the positive energy in matter, radiation, and dark energy, making the total energy exactly zero. If total energy equals zero, the universe can emerge from a quantum fluctuation without violating energy conservation. Quantum mechanics permits such fluctuations through the uncertainty principle. Energy can fluctuate by an amount proportional to Planck's constant divided by the time duration of the fluctuation. For extremely brief moments, large energy fluctuations can occur. A universe with total energy zero could appear spontaneously from nothing because it wouldn't actually be creating net energy. It would be creating equal amounts of positive and negative energy simultaneously. This process becomes easier to visualize through the inflation hypothesis. The very early universe might have been dominated by a peculiar quantum field stuck in a high-energy state. This field would have negative pressure, acting like a cosmological constant. Negative pressure in general relativity produces repulsive gravity, driving exponential expansion. As space expanded exponentially, the field's energy filled the newly created space. But the gravitational potential energy of all that expansion became increasingly negative, potentially matching the positive energy being created. The total energy remained zero while the universe explosively grew. When inflation ended, the inflaton field's energy converted into ordinary matter and radiation through a process called reheating. The universe transitioned from cold and dominated by the inflaton's energy to hot and filled with particles. This conversion represented a change in the form of energy, not a creation of net energy. The positive energy in all those particles balanced against the negative gravitational potential energy of their mutual attraction and the energy in the expansion itself. The expansion continues today, driven now by dark energy rather than the inflaton. As space expands and creates more dark energy, it simultaneously creates more negative gravitational energy. The balance maintains. Calculations attempting to determine the universe's total energy remain uncertain due to theoretical difficulties in defining energy globally in general relativity, but they suggest values consistent with zero. The universe might genuinely contain no net energy at all, despite appearing to contain vast amounts. This resolution of the creation paradox relies on accepting that space itself is a physical entity that can expand, contract, and possess properties like energy density. Empty space is not truly nothing. It seethes with quantum fluctuations, possesses vacuum energy, curves under gravitational influence, and expands according to Einstein's equations. The nothing from which the universe emerged wasn't philosophical emptiness, but rather the quantum vacuum, a state with structure described by quantum field theory. Some physicists go further, suggesting the universe is inevitable rather than improbable. If quantum mechanics permits fluctuations that create universes with zero total energy, and if such fluctuations face no barrier preventing them, then universes must appear. Our existence requires no external creator, no initial conditions carefully selected, no fine-tuning beyond what's needed for the mathematical consistency of physical laws. The universe bootstraps itself into existence through quantum processes operating on vacuum states. The expansion plays a crucial role in this story. Without expansion, the universe couldn't maintain zero total energy while containing matter and radiation. The positive energy in particles needs to balance against something, and that something is the negative energy associated with gravitational binding and cosmic expansion. Expansion also explains why the universe began hot and dense rather than cold and sparse. If you start from nothing and spontaneously create a universe, you create it in its minimum energy state, which for a universe with our physical laws means an extremely hot, dense plasma that then expands and cools. The creation paradox thus finds resolution not in theology or philosophy, but in the mathematical structures of general relativity and quantum field theory. The universe expands into nothing because it is fundamentally made of nothing, a zero-energy fluctuation that's separated into positive and negative components, with the positive appearing as matter and the negative as gravitational binding. The expansion perpetuates this separation, creating more space filled with more positive energy balanced by more negative gravitational energy. Something came from nothing because something and nothing aren't as different as our intuitions suggest when gravity enters the picture. The universe is nothing, just rearranged into a form that looks like something. And that looking, that rearrangement, is precisely what we call existence, the multiverse nothing. Our universe, expanding into its own version of nothing, might itself be embedded in a vastly larger nothing, populated by countless other universes, each one a separate bubble of space-time with its own physical laws, its own history, its own expansion into its own localized nothing. This multiverse hypothesis emerges not from science fiction, but from taking seriously the mathematics of cosmic inflation and quantum mechanics. If the processes that created our universe can happen once, they can happen infinitely many times, each occurrence producing a separate universe that expands independently, never touching or interacting with the others, isolated by barriers more absolute than any distance. The inflationary hypothesis that explains our universe's early expansion contains within it the seeds of eternal inflation. During our universe's first fraction of a second, a quantum field called the inflaton drove exponential expansion, stretching a tiny region to macroscopic size in less than 10 to the minus 32 seconds. This inflation ended when the inflaton field decayed, converting its energy into the matter and radiation that filled our universe. But in the broader inflaton field extending beyond our universe, inflation need not have ended everywhere simultaneously. Quantum fluctuations in the field would cause it to decay in some regions while remaining in the high-energy state in others. Regions where inflation continues expand exponentially fast. Regions where it ends become universes like ours. But the expanding regions grow so rapidly that they always produce more volume than the decaying regions consume. The result is eternal inflation, an ongoing process where the inflaton field keeps spawning new universes forever, each one a bubble of decayed field surrounded by eternally inflating space. These bubbles expand into the inflating space around them, but they can never catch up to the exponential expansion, so they remain isolated, unable to interact or communicate. Each bubble universe would have its own properties determined by how the inflaton field decayed in that region. The fundamental constants of nature, the strength of gravity, the mass of electrons, the cosmological constant, might vary from bubble to bubble. The number of spatial dimensions, the types of particles that exist, even the laws of physics could differ. Most bubble universes would be sterile, incapable of forming stars or galaxies or any complex structure. Some might collapse immediately, others might expand so rapidly that matter never condenses. Our universe, with its particular combination of properties permitting stars, planets, and life, would represent one possibility among infinitely many. The nothing between these bubble universes would be quite different from the nothing our universe expands into. It would be inflating space, filled with the inflaton field's enormous energy density, expanding exponentially and creating new volume faster than the bubble universes can claim it. This inflating medium serves as a sort of background or substrate from which bubble universes emerge, though calling it a substrate risks misleading analogies. The inflating space has no permanent features, no structure, nothing that persists. It simply expands, occasionally spawning new bubbles through quantum decay of the inflaton field. Observational evidence for this multiverse remains indirect and controversial. We cannot observe other bubble universes directly because they lie beyond our cosmic horizon, separated by inflating space expanding faster than light. Any signal from another bubble would be infinitely redshifted before reaching us, but cosmologists have proposed several potential signatures. If our bubble collided with another bubble during the early universe, it might leave patterns in the cosmic microwave background radiation's circular temperature variations marking where the collision occurred. Searches for such patterns have found nothing conclusive, placing limits on how common such collisions might be. The anthropic principle also enters discussions of the multiverse. If infinitely many bubble universes exist with varying properties, observers can only arise in universes with properties permitting life. This might explain why our universe's fundamental constants appear fine-tuned for life. They're not fine-tuned, rather, we necessarily find ourselves in one of the rare bubbles where the constants allow complex chemistry in stable stars. The vast majority of bubbles would be empty or hostile, but with infinitely many bubbles, even extremely rare combinations occur infinitely often. String theory offers another route to multiverses through the landscape of possible vacuum states. If string theory correctly describes fundamental physics, it permits roughly 10 to the 500 different vacuum states, each corresponding to different values of fundamental constants and different physical laws. Which vacuum state dominates in a given region of space might vary, creating a patchwork of different physics across the larger inflating space. Our observable universe would occupy one such region, with one particular vacuum state, surrounded by regions with different states. The multiverse hypothesis troubles some physicists because it potentially explains too much. If every possible universe exists somewhere, any observation becomes compatible with the theory. The cosmological constant, particle masses, spatial dimensions, all can be explained by saying we observe these values because we exist in one of the rare bubbles where these values permit observers. This reasoning, while logically sound, doesn't predict anything. It accommodates any observation after the fact, rather than making testable predictions beforehand. Yet the mathematics leading to eternal inflation follows from well-established physics. Quantum field theory, plus general relativity, applied to an inflating universe, naturally produces eternal inflation, unless special conditions prevent it. The multiverse might be an unavoidable consequence of our best theories about the early universe. Our universe expanding into its own nothing might be one of infinitely many such expansions, each creating its own isolated bubble of existence in an eternally inflating background that itself might qualify as nothing, no structure, no permanence, just expansion, punctuated by occasional bubble formation. The nothing our universe expands into would then be a local nothing, specific to our bubble, while beyond it lies the larger nothing of eternally inflating space, itself giving rise to endless other nothings as new bubbles form and expand. The final answer, the universe expanding into nothing, means there is no external arena, no surrounding space, no container holding our cosmos. The universe constitutes the entirety of space itself, with nothing referring not to some region beyond, but to the absence of any beyond whatsoever. This isn't a limitation of our knowledge or technology. We're not simply unable to observe what lies outside. There is no outside. The concept itself breaks down when applied to the universe as a whole. Space is defined by the universe. Beyond all of space cannot exist because beyond is a spatial relationship that only has meaning within space. The universe is all there is, and its expansion requires nothing external because expansion describes the evolution of space itself rather than motion into something else. Every attempt to ask what's outside the universe reveals the question's internal contradiction. Outside is a location, a place beyond some boundary, but location only exists within space, and all space is contained within the universe by definition. Asking what's outside all of space is like asking what number comes before the concept of numbers, or what color surrounds colorlessness. The question attempts to apply concepts beyond their domain of validity. Our language evolved to describe objects within space, not space itself, so every phrase we use to discuss the universe's extent carries misleading implications. The balloon analogy helps here one final time. A two-dimensional being living on a balloon's surface could map their entire universe, measure distances between points, observe how the surface expands as the balloon inflates. They might ask what lies beyond their surface, what the balloon expands into. From our three-dimensional perspective, we see the balloon sitting in a room, expanding into the air. But for the two-dimensional being, there is no beyond. Their universe is the surface. The three-dimensional space in which we visualize the balloon is inaccessible to them, imperceptible, and not necessary for describing their universe's geometry or evolution. Our situation parallels theirs. We live in three spatial dimensions, observing our universe's expansion. We might invoke a fourth spatial dimension for visualization, imagining our three-dimensional space curving through it. But this fourth dimension is a mathematical convenience, not a physical place. Our universe's geometry can be described entirely through intrinsic curvature without reference to any embedding space. General relativity formulates space-time as a four-dimensional manifold, three space dimensions plus time, that curves and evolves according to its energy content. No fifth dimension is required or implied. The expansion of the universe represents a change in the metric, the mathematical object that defines distances. When cosmologists say space expands, they mean the metric changes such that distances between non-gravitationally bound objects increase over time. This increase requires no external space to accommodate it. The metric simply evolves according to Einstein's field equations, which relate the curvature of space-time to the distribution of matter and energy within it. These equations form a self-contained system. They describe how space-time curves and evolves without invoking anything external. The Big Bang illustrates this self-containment most clearly. The universe did not begin as an explosion in pre-existing space. Space and time themselves began at the Big Bang. There was no before, no elsewhere, no outside into which the explosion could expand. The entirety of space existed in an extremely hot, dense state and has been expanding ever since. Every point in space today was once adjacent to every other point at the Big Bang. The expansion separated these points, creating distance where none existed before. But this creation of distance happened within space itself, not by space expanding into something else. The concept of nothing that we've explored throughout this journey thus has a precise meaning. The nothing into which the universe expands is not a place, not a void, not empty space waiting to be filled. It is simply the absence of anything outside the universe. There is no outside because space itself defines inside. The universe contains all spatial relations, all locations, all distances. Beyond this, beyond all of space, lies not some exotic realm, but rather the meaninglessness of the question itself. Outside doesn't exist, because existence is a property of things within the universe. This understanding transforms how we think about cosmic expansion. Rather than picturing the universe as a growing sphere pushing into surrounding emptiness, we should picture the metric of space changing, distances increasing, galaxies separating, all described by mathematical equations that reference only the universe's own internal geometry. Space doesn't need anywhere to expand into, because expansion is not motion through a background medium, it's an evolution of the background itself. The philosophical implications extend far. The universe is not embedded in some larger reality, it is reality. All that exists, all that has existed, all that will exist, occupies this one cosmos. The vast expanses between galaxies, the quantum foam of empty space, the dark energy driving accelerated expansion, all of it occurs within the universe, which is also all of space and time. There is no larger context, no external perspective, no view from outside, because outside is a concept that doesn't apply. This completeness and self-containment carries a certain austere beauty. The universe requires nothing beyond itself. It is whole, complete, sufficient. The equations describing its evolution reference only its own internal properties, the distribution of energy, the curvature of space-time, the values of fundamental constants. Physics studies this self-contained system without needing to invoke external causes or external spaces. The universe is, as cosmologists sometimes put it, a closed system in the deepest possible sense. Not closed by boundaries, but closed by being all there is. The expansion into nothing thus represents the universe being thoroughly and completely itself, nothing more, nothing less, nothing beyond. Space grows because the metric evolves. Galaxies separate because space expands. Dark energy accelerates expansion because its energy density remains constant as space grows. All of this happens within the universe because there is nowhere else for it to happen. The nothing is simply the absence of anywhere else. The universe expands into nothing because nothing exists for it to expand into. The universe is all there is, and that all requires no container, no arena, no background. It simply is.